our work when we were doing differentiation, we learned about differentiating this function here. So we're now going to learn about integrating back to this. But I thought I would use the examples they had in the book, but we'll just do them on the board and work through how we differentiate this. Okay? So it's all in your textbook, but we'll work on this together on the board. So we've got y equals the inverse tan of x over a, and our first step is we're going to take tan of both sides, and that gives us that. We probably don't need to break it anymore, right? And then we can say, all right, well that's the same as a tan y is equal to x. And at this point, we're going to do a bit of a review of our differentiation, right? So we're going to differentiate with respect to x, so we're going to do some implicit differentiation. Remember that from a few chapters back? So it's real easy to do this side. That's just going to become 1, isn't it? Right, but when we differentiate this, you notice that there is no x. So we would say this is going to be a tan y d dx, right? That's our first step. But another way of writing this is a tan y d dx, d dy, that's a bit dodgy, d dy, and then dy dx, right? Alright, it's the same thing. And then we can say, oh, a is a coefficient, right? So that's going to stick around. So what is this? Tan y d dy, if we're differentiating with respect to y. What's when we differentiate tan y is?
Sec squared y.
Yes, very good. So sec squared y dy dx. So that sticks around, doesn't it? So we've just done that bit. Equals 1. And the next step would be to go a times dy dx is equal to 1 over sec squared y. Okay, now we can write this another way. We've got our rule where sec squared y is equal to 1 plus tan squared y. So now we're at 1 over 1 plus tan squared y. And at this point we can go, hang on a minute, up here we worked out what tan y was, so we can insert this into here. So this becomes a dy dx equals 1 over 1 plus x over a squared. So that's an a. Alright, so next line, a, maybe just a bit down so we're not in the light there, dy dx equals. Now, we can simplify this to 1 over 1 plus, and it's x squared over a squared. And we want to simplify this again, so maybe I will go a dy dx equals 1 over, and we're going to have a squared plus x squared all over a squared. So I've made this have the same denominator, but when we've got a whole number over a fraction, what happens? That goes to the top. Last step, to get rid of this a, dy dx equals this divided by a, which is going to give us a over a squared plus x squared. Are you happy with that last step? So when I divide, it's the same as timesing by 1 over a, and that will cancel out one of those. So this leads us to the rule that we're going to learn, and you are given this rule, the integral of tan minus y. Oh, sorry, not that. The integral of a over a squared plus x squared is equal to tan inverse x over a. You're not quite given this, you're given something slightly different. You're given this in the exam. Difference between this and this, just you've got rid of that a, so it's going to be 1 over a. Okay, so this is a formula, will be in your formula sheet. Okay, so we've just proved this, which you're given. You don't need to be able to prove it, but you can see this makes total sense. Okay, so when you have a fraction, when you have 1 over, and you've got some constant squared plus x squared, you can integrate it like this. And that's what we're going to do today. That's the first step. Step 1. What do we want to do?
10 on both sides.
Yes, fantastic, he's in. Okay, 10y. You just wanted to do that step, right?
Yep.
Yeah, so now I'll ask someone else the next step. Okay, right, what's the next step? Any ideas?
Differentiate using ddx.
Yep. Maybe we want to get this over first, but you're totally right. We could do that now, but then we'd end up with some annoying stuff, so let's just do this, right? And then differentiate with respect to x, so we're going to do some implicit differentiation. Right, this bit, this is a recalling to mind what we did earlier on, so Griffin, what could we change this to?
So tan y d dy dx.
Okay, and I don't think in the example they give you it all in this detail, but it's good to refresh our memories of what we're actually doing. Okay, so next line should be, this becomes, any ideas what we're going to do next? Should we get this across? Yep. And then another way of writing this using our thing, what do you call it? I, it starts with I and I can't remember it. One of those rules. 1 plus 10 squared y, it's Monday. Okay, and then we can replace this, knowing that this is equal to this. Okay, so my next line up here is going to be 1 over b dy dx, and then I'll have 1 over 1 plus 10 squared y is going to be this squared, so it will be b squared x squared, or bracket bx squared. Okay, cool, and then we want to get rid of this b thing here, don't we? So dy dx equals b 1 plus b squared x squared. Okay, and therefore we can say that the integral of b 1 plus b squared x squared is equal to and we probably should say plus a constant, right? Now, I think in the book they give you something like this, and therefore we're just going to have to get rid of that there. So we'll have a 1 over b, and that is that. So those are the, this one you have to memorize, okay? So do memorize it, will make life easier. The other one will be given to you in the formula sheet. Which one of these two does it look like to you? First or second one, do you reckon? What do you reckon? Okay. So we could say that a in this case must be 2, right? Because square root 4. So we could say, well, this is going to be 1 over 2, and then tan inverse, x over a being 2. Last step, what have I forgotten? Plus c. Now the trick is, that's real easy, right? The trick is when you see something like this in an exam, to remember that that's what you're trying to achieve, right? And not go off on some other tangent. Okay, let's try another one. Why don't we try something like, let's try number 3a. So number 3a, we've got this. We're trying to find integral of 1 over 3. I think it's 3. no, 1 over 1 plus 3x, okay, 1 plus 3x squared. This looks a bit nasty. Does it look like any of those to you? Yep, the second one. Okay, cool. Let's do that. The second one. So it's going to be equal to 1 over b. Now, what is b in this case? B squared. So this is b squared. So b must be square root 3. And then we're simply going to have inverse tan of square root 3 times x plus c. Okay, that wasn't so bad after all, was it? Okay, those are okay. Let's say we go to something a little bit more tricksy, like 4a. So what have we got for 4a? Well, that's cruel. What is it? 1 over 4 plus 9x squared. Which one does it look most like to you? The second one? There's a little bit of a slight issue. What's the slight issue? The 4. So what we can do is we can go, well, this is equal to 1/4, yeah, times, what's this next bit going to be? 9 over 4 x squared. Are you happy with the logic on that? 4 times this will give us a 4, 4 times this will give us the 9x squared. Okay. So we're going to have 1/4 times. Now, in this case, we've got a b squared is 9 over 4, so a b must be the square root of 9 over 4, which is 3 over 2, but remember I've got to do 1 over that, so it's 1 over 3 over 2. What's another way of writing 1 over 3 over 2? 2 over 3, so let's do that instead, because that makes it a lot easier. 2 over 3. And then tan inverse, and then I'm going to have bx. Now bx is going to be 3 over 2x, because this is b squared, so b must be the square root of that. So the reason we've got the flip there is because if we look at this, it's 1 over b, and 1 over 3 over 2 is the same as 2 over 3. So then we can simplify this to 2 over 12, which is 1/6 inverse tan 3 over 2x plus c. Alright, okay. So what does this look like to you, Griffin? Type 1 or 2?
Type 1.
Perfect, okay. So, we can probably go straight into our square brackets, I think. What's a going to be? Any ideas, anyone? What do you reckon, Rebecca?
3.
Okay. So 1 over 3 inverse 10. What are we going to have here? X over a, so x over 3. And we don't need a plus c because it's a definite integral. And we put these numbers at the edge of our square brackets. Next line. Oh, what do we want our calculators to be set to when we do this? They must be set to radians. Okay. So we're going to go 1/3 inverse tan of 1, right? Inverse tan of 1, is that pi over 4? Over 4. No? What is it?
Pi over 12.
Pi over 12. Oh, wait. This bit here?
Oh.
Is it pi over 4? I think the final answer is pi over So, yep. And then the next bracket is going to be 1/3, sorry, you're ahead of me, times inverse tan of -1. So what is that? -pi/4. Okay, so like you were saying, we're going to have pi/12 minus pi/12, so we're going to have 2pi/12, or simply we could say this will just be pi/6. And hopefully that is